Entonces, comenzamos con esta sesión de la tarde con la charla de Xavier Gómez-Mont.
Cómo no, muchas gracias. Bueno, quiero agradecerle a Jacob que me haya invitado y, por supuesto, Samuel fue para mí una gran inspiración. Yo no soy descendiente de él, ni mi apellido Gitler, ni Hammer, pero tenemos un ascendente en común que sería Lefschetz. Entonces, él jaló a la parte de topología algebraica y yo jalé a la parte de geometría algebraica y a diferencia de Ernesto, que habló en la mañana, mi geometría algebraica es más clásica que hipermoderna. Entonces, para empezar en el contexto de la topología, a veces la topología funciona muy bien y a veces no funciona. Y entonces tiene uno que hacer algo para que funcione la cosa. Entonces, dejen empezar con un tema que se llama lápices de Lefschetz. Lápices de Lefschetz. Entonces, estas son expresiones en dos variables complejas que son dos polinomios de grado D. Son polinomios de grado D. Y entonces esto lo vemos como que nos va a dar una función de C2 en C. Y entonces queremos, si esto lo llamamos F, o sea, es una función racional. De hecho, vine aquí a dar a C infinito, a la esfera de Riemann. Y entonces, en los puntos donde no está definido, es como nos dijo nuestra abuelita, que es donde 0 entre 0. 5 entre 0 es infinito, pero 0 entre 0 es lo que no podemos hacer. Entonces, esto lo que vamos a ver es que vamos a agarrar los valores que toma la F, y entonces esto nos va a dar una descomposición, nos da una descomposición de C2 como la unión de las F a la menos 1 de lambda. Y entonces la figura típica es que esta es una de las curvas, este sería la que es F igual a 0, esta es la que es G igual a 0, y entonces todas las otras pasan por aquí, y entonces si le quita uno los puntos donde las dos cosas valen igual, o lo que es lo mismo, explota uno, hace uno un blow up. Un blow up es como tomar coordenadas polares. Please, here's your place. No, here, we put a place for you. ¿Sigo en español o hago en inglés? So I'm beginning with going back to a classical topic, which is this thing of Lefschetz pencils. So we have a rational function, which is the quotient of two polynomials in two variables of degree D, and this decomposes C2 into a disjoint family of the level curves. And then if lambda denotes the set of points where f is equal to g is equal to 0, which would be these common points, and if instead of considering C2, we consider CP2, so since these are polynomials we can compactify, the picture we obtain is the following. We have the Riemann sphere. Over a general point of the Riemann sphere, we will have this fiber. So this will be a Riemann surface of genus G, where G is 1/2 times D minus 1 times D minus 2. And then there are, and then we have these points lambda that we deleted. So we have the fiber is a compact Riemann surface minus a finite number of points. And then, we have a finite number of critical values. So sigma are the critical values of F, of this big F. So a critical value is a point where a partial of F with respect to C1 is equal to partial of F with respect to C2 at the point P is equal to 0. At the points where one of the partial derivatives is not 0, then we can apply the implicit function theorem, and then that says that the fiber is smooth. And it's not only smooth, but in a neighborhood, all the fibers are smooth. This is called a float box. So this, by the implicit function theorem that all of us have seen in elementary courses, calculus courses, it is true over the complex number, and this is the picture. So if we consider the Riemann sphere minus the critical values, and we consider F minus 1 of sigma, of C bar minus sigma, then this becomes a fiber bundle, a locally trivial fiber bundle, which means that if we take a neighborhood and we take the inverse image restricted to this neighborhood, is topologically a product. So this is in the C-infinity category. This is a C-infinity locally trivial fiber bundle. And then one thing which is important is the following situation. So the general critical point in C2 is, after a change of coordinates, the function f of W1, W2 equal to W1 squared plus W2 squared. And what this is that over 0, it is 2 lines, and then outside of 0 is something like this. So this is la guillotine. So we have a small neck, and we are squeezing the neck. So here, see, usually we are accustomed to think over the real numbers, or some of us are accustomed to think over the real numbers, but over the complex numbers, then here we have 0, here we have this value, and so we have something that looks like this, and then over here we have something that looks like this. But then when we are approaching, so this over here is called the vanishing cycle, and when we arrive at the critical point, what happens is that the vanishing cycle is being squeezed to 0. So there is this, there's a vanishing cycle being squeezed, but there's something very interesting in the sense that if we remove 0, the bundle we have over the disk minus 0 is not the trivial bundle. Even though the fiber is always this, so this is like an annulus. When we go around and we come back, we don't come back with something which is isotopic to the identity. And what happens is the following, is that if we take here something that looks like this, and we go around and come back, then this will come back like this. So we twist, we twist. So there's this twisting phenomenon. Every time you have a critical value, so there's something happening. There's something happening. There's a vanishing cycle, and then there is this non-trivial monodromy. Now, in this case, what happens is the following. What's typical is that instead of removing the points, we blow up the points so that we have a compact Riemann surface over each of the fibers. And then, so here we have these critical values. And then we have this bundle structure, this locally. So this means that, you know, this, the topologist would do something like this. You take a path, and then you come back, and then you go like this, and then you go like that. So you take a representation of the fundamental group of the complement of the Riemann sphere minus the critical values, and this is acting on the endomorphisms of the surface. And this describes completely the bundle. Now, this F is given by some coefficient. So here we have sum of Aij, C1 to the I, C2 to the J, sum of Bij, C1 to the I, C2 to the J. So we have this space of parameters, which is A1 or A or D0 up to B0D. So this is some Cn. And for every point, we have a picture like this. So here we put the CP2, and then here we have this picture. And then we have this picture. So one might ask, what's the difference between the picture we obtain from these coefficients from the picture that we obtain from these other coefficients? So in principle, from an algebraic point of view, we have the group of automorphisms. So the group of automorphisms of CP2 by holomorphisms are the projective linear transformations. So this is PGL3C, which is an 8-dimensional group. So this means that we might change coordinates of projective plane, and then we get the same picture, the same, because it's only a change of coordinates. But we like to see if they are topologically the same, And so the fact will be the following. See, here we have this critical value, so this means here we squeezed a cycle, but now we might think from this point of view, instead of squeezing this guy, let's squeeze the other one. And so the thing is the following, that in a neighborhood of a critical value, all the curves, all the fibers are isotopic. So this means that if I squeeze this one, or if I squeeze this other one, there is an isotopy that sends one to the other. And so the conclusion of this is that for general point in these AI BIs, there is only one topological model. So even though there are many different rational functions, and even though they are not biregularly equivalent, anyway, we will find for a set, we exclude some set where we have some more complicated singularities, and then for any 2 points that we have here CP2, we would have the fiber structure here, the fiber structure here. There is a homeomorphism sending CP2 to CP2, which sends the fibers to the fibers. So there's only one model. So this is classical Lefschetz theory. Now I want to generalize this to the following situation. So, so in the previous case, when we had f over g, we apply the derivative. And so this becomes g times df minus f times dg. And here we divide by g squared. So we get rid of this. And this is a one form. A one form. So more generally, let omega be equal, and then we put here sum of aij's c1 to the I, c2 to the j, dc1 plus sum of bij's ci, cj, c1 to the I, c2 to the j, dcj. So this is the space of one forms. So here now we have this space. This is given by these coefficients ai and bi's. Is some parameter space. And then for every point that we have, we're going to construct a geometric object associated to this one form. And so the geometric object is the following. So given any point P, omega of P is a map from the tangent bundle at P to C2 to C, and so we can consider the kernel of omega P. So this will be given in the tangent plane, is specifying a line, and so we have a distribution of lines in CP2, and this is at the points where omega of P is different from 0. We get a distribution of lines, and then the definition is the following. So the foliation associated to omega, so this is the foliation, the holomorphic foliation with singularities. The singularities are where the kernel of omega, where omega of P is equal to 0. So, so this will be the integral curves, complex curves, tangent to the distribution specified by omega. So the theorem of existence and uniqueness of solutions of differential equations with complex coefficients guarantees that through every point where omega of P is not equal to 0, we will have a flow box. Looks like this. And then we take here another point, and then we have another flow box. And so we can put on these flow boxes the following topology. Here we put the usual topology, and we put the discrete topology on the transversal. And then we take the connected components in this topology, and so these will form the leaves of the foliation, and then we will have that CP2. Here I'm putting it in C2, but since everything is polynomial, you can extend it to infinity in a very simple way. So CP2 minus the set of points which are the singularities of the F omega will be decomposed as a disjoint union of L alpha will now be some Riemann surfaces but in general, they will not be compact. So this means that you come around like this, and then you don't close up. And then you move around these columns, and then you finish getting a mess. So the leaf is moving all around. And so this case, which I explained to you, this Lefschetz pencil, was a very specific case where the leaves, where I did this form. This is very special, and this only form is sub-family, which are the ones which have a first integral. Usually they don't have first integral, and then one wonders if, like in the case of Lefschetz pencil, is there just one topological type? Okay, so it's a very natural question. So people have investigated this question, and the answer is no, that actually the contrary is the case, in the sense that if you have two which are topologically the same, if two general elements are topologically the same, which means that there is a homeomorphism from CP2 to CP2, which sends the leaves to the leaves, then actually you can find a biholomorphism that sends one to the other. So in that sense, if you move a little bit the equations, you're going to change the topology of what's happening. So in that sense, in Lefschetz's picture, it was very boring because everybody looks topologically the same. Here it's very interesting because everybody looks different. Okay? Now, for some time, this result that I'm saying is only true for general elements. So these general elements, it does not mean that there could be some subvarieties in here which do have the same topological type or are related in some topological way. So that's what I want to explain. I want to explain that in these parameter families, myself and other colleagues, we have found subvarieties of arbitrarily large dimension when the degree grows, where they're not exactly topologically the same, but almost topologically the same, and we will explain what's this almost topological thing. So now let me state a definition. So I'll do just for a one-dimensional parameter. We have t, some complex parameter, and we have omega t. So it's a family of these forms A sub t of C1, C2, dC1 plus B of t of C1, C2, dC2. So for each one, we have a copy. I'll do it in C2. We can extend it to CP2. So in C2, then we have this picture over here. And then we move the parameter. And we have a different picture. And here we have a different picture. So we have a one parameter family of these one forms. Now, we will say that this one parameter family is an unfolding if we can find a CT of C1, C2 in such a way that when we consider the form omega t equal AT dC1 plus BT dC2 plus CT dt. So this is a one form, but now in three variables. It is integrable. And integrable means that omega t exterior d omega t is equal to 0. So this is a 3 form in C3. When this condition is true for a one form in 3 variables, it means that given a point where omega t at p is different from 0, we can find a neighborhood in C3, and then we have local charts where we have a foliation with leaves of complex dimension 2. So we actually have a foliation of dimension 2 such that when we restrict here, is cutting this family omega t. So in some sense, there is this relationship between the different omega t's. And so then one says, well, here you have the problem that you have to find such a guy like this. So what we're going to do, we're going to put ourselves in a geometric situation where we will have the A's, the B's, and the CT's. So we have the unfolding. And then we will analyze what happens with this topological type. No voy a poder pasar español. Now, when we do have an unfolding, what happens is the following. See, the thing is that since the leaves here, they can be extended to the thing over here, then this means that what you have over here, you have similarly over here, because if you follow a path in a leaf here, then the leaf, since it extends into this other dimension, then you can transport this path into the near one. And so this is saying that these two things are very similar. So in some sense, since we want to prove that this, under these assumptions of having of being an unfolding, then what happens here is the same that what happens over here. Then we have that in an unfolding, we do have topological equivalence. Now, this is not true. So we are proposing the following definition for that's so here's where I tell you that sometimes topology is not convenient.
The derivative doesn't incorporate the time.
Which one?
The derivative
it incorporates the time.
The total the round derivative is without t, or is with t.
Well, no, all of them are with t, with C1, C2, and t.
No, but the derivative operator.
Is dt.
One on the right. That derivation.
No, this is derivative with respect to C1, C2, and t.
No, and t.
And t. So this means that in the three-dimensional space, it's an integrable one form. So this condition of integrability is called Frobenius integrability condition. And then it means that at the points where the thing is non-zero, then we find coordinates in such a way that it looks like this. So we can change coordinates and put coordinates omega 1, omega 2, omega 3. And in these coordinates, our form omega looks like d omega 3. So lleva uno la ropa sucia a la planchaduría y planchan. So, nos planchan las camisas y sale todo muy planchadito. That's what this says. So things are being all screwed like this. but you can change coordinate and then it looks like this. And this is the condition. So, we're going to set up a definition which will work for us. And so the definition is the following. So we have f of omega 1 and f of omega 2 are U topologically equivalent. The U comes from unfolding if there exist open sets U1 up to UR and V1 up to VR and a homeomorphism phi from CP2 minus the union of the UIs into CP2 minus the union of the VIs so which is sending the foliation of omega 1 to the foliation of omega 2. So this is a homeomorphism outside of some boxes. We call these boxes, outside of some boxes. And then in these boxes, UI, we want that there exists a function Fi to the disk and functions Vi from GI to the disk. Delta is the unit disk in C. In such a way that the hypothesis, the conclusion of Milnor's vibration theorem is true. So what does that mean? This means the following, is that here in delta, we have a finite number of critical values, and then outside of we have some Riemann surface with boundary, and then if I take the complement of this finite number of critical values, then I have a fiber bundle. And then the fiber bundle on the boundary is the trivial bundle. Is a trivial bundle. And so this extends even over the critical points to the trivial bundle over the critical points. And then over here, I have the situation that I have some fiber, which is some singularity. I have some singularities. And then here I have similarly, but perhaps here the number are different. The number of points that I have to remove are different, but what I need is that in the complement of this finite number of points and this finite number of points, the fiber bundle is homeomorphic. So I'm going to remove this piece and glue this piece. So what I'm saying is that they are the same outside of some set, and then on some boxes you are allowed to do this kind of surgery. Now let me explain why this is going to be necessary. So we are here in CP2, and so we have this leaf, and then this leaf goes and then comes back, and then it has a critical point. It has a critical point. No, so here in the neighborhood, if this is an ordinary critical point, this will look like f of omega 1, omega 2 is equal to omega 1 squared plus omega 2 squared. Now here, so it was this topology I explained of the necks, of the necks. We have this picture here with this non-trivial monodromy going around. Now, if I look at a leaf which is nearby, and I want to make the vanishing cycle not on this leaf, but on the nearby leaf. But then if this nearby leaf is doing something very different from this one, then I am not going to get a homeomorphism, which is going to send me, see, if I just change the foliation in this neighborhood and change the singularity from this leaf to this other leaf that I can do locally, then I am not going to be able to obtain a homeomorphism which is leaf preserving, which transforms one foliation to the other, because in some sense, if I delete the neighborhood, I am marking a leaf, because this is the one which has a singularity. If I mark a different leaf, if it's doing something very different, then I cannot find a homeomorphism. In the case of Lefschetz pencils, it was true because if I have a fiber and I have a nearby fiber, they are isotopic. So I can change the singularity from one to the other and nothing happens. In this situation, I cannot do that and keep having a homeomorphism. So what this definition allows is to allow to move the singularity from one leaf to the other leaves. And then it's a necessary condition for finding some kind of topological equivalence. Now, let me explain. ¿Cómo vamos de tiempo? 20 minutes. Now, let me explain to you the situation that we arrived at. And I think this is a very interesting situation. So I'm going to explicitly exhibit these families where this phenomena is happening, and it is the following. So we go from CP2, a map from CP2 to CP2, which is given by F1 or F0 double point F1 double point F2, where Fi are polynomials of degree E, which have the property that I put F0 equal to F1 equal to F2 equal to 0 is the empty set. As everybody knows, CP2 is C3 minus 0 divided by the equivalent relation given by multiplication with a non-zero scalar. So this hypothesis, what this means is that this is giving me a map from C3 to C3, and the only point which is being mapped to 0 is the 0 point. So if I delete 0 from here and 0 from here, I get a map from CP2 to CP2. This means the following thing. This is the same as saying in homogeneous coordinates. I'm looking at a map from C2 to C2, which looks like F0 over F2, comma, F1 over F2. So this is a rational map of degree E. And if I put this condition, then this gives me a holomorphic map from CP2 to CP2. If I call this F, this is phi sub F. And so this phi sub F is a branched covering map, which is E squared to 1. So this means the following. So here I have CP2. Here I have my function, this phi sub F. So I take, I write it in homogeneous coordinates like this. And so I write the derivative of phi, and then I take the determinant, and I put equal to 0. So this is some polynomial of degree 2e minus 1, and so this defines some curve. On the complement of this curve, the derivative is non-zero, the determinant is non-zero, and so I can apply the inverse function theorem. And so this says that outside, it will be a local biholomorphism. And so if I push forward, so this set here is called the ramification locus, is a curve. The image under the map of this RF is called the branch locus, is another curve. If I pull back the branch locus, I will get a map which goes from CP2 minus the inverse image of the branch locus into CP2 minus the branch locus, which is a covering map E squared to 1. A covering map in the sense that if I take if I take a point, then there is a neighborhood, and the inverse image, there will be some neighborhoods, and then I have my covering transformations that send one to the other. And so now here I'm going to put an omega f, an omega. So here I'm going to choose an omega, choose an arbitrary. And so here I have some of this picture here. So I don't know, it might be very complicated. And then I'm going to pull back the form over here to phi f minus 1 of omega. So this gives me a 1 form here. And the trick I'm going to do is I'm going to move the f in the family of maps. So I fix the guy over there and I pull the different ones. And so in some sense what I get over here is the same picture that I had over here, but now I have E squared copies of the same picture. And of course I have to understand what's the effect of the branch curves with respect to the foliation. And so the claim is the following, that if I put in red this branch locus of f, so if the foliation is transverse to the red, then the inverse image, it will have smooth points. And if it is tangent, then it will have a singularity of this form which I explained. If it's a simple tangency, then I have one of these simple singularities of singularity theory, this omega 1 squared plus omega 2 squared. So I am doing this squeezing of the vanishing cycles, but not to the fibration, to the foliation. And the thing is that when I move the f's, then this branch locus will be moving, and so this means that this tangency, it will be moving. So if I move in a parameter the f's, then here the tangency will be moving, the leaf will be moving, and I'm changing the squeezing from one leaf to the other leaf, and so they cannot be topologically the same, but they will be the same in my definition. So this gives, when we consider families of maps of this form, and we consider forms, so the theorem is the following. So this is a theorem done jointly with Bonatti, with Gallego, and with González Villa, and myself, that says that for general f in this family of maps, phi f star of omega will be U equivalent to phi f prime star of omega. And this will be for any omega. So any picture I have over there, and actually we can be much more precise what we mean by general. It means that this tangency between the branch locus and the thing is general. But even more interesting, so this gives very big examples of foliations, which are unfoldings, and the different unfoldings satisfy this definition we are proposing of equivalence, which, as I mentioned, is weaker than topological equivalence, because we are allowing to move the vanishing cycle from one leaf to other leaves that have different topological behavior in the manifold. Now, more interesting is the case where we have this F, which is given by F0, F1, and F2. But we assume that the set of points where F0 is equal to F1 is equal to F2, equal to 0, is a discrete set of points. Because in this case, so we have this finite set of points where the three vanish, and if I take a general point over here and I take its inverse image, so here in this case, this phi of f will be a function from CP2 minus this set of points. These are called the indeterminacy points of the map into CP2, which now if I take a general point and I take the inverse image, then there is associated to each of these critical points a number L1, L2, L3, which corresponds to the multiplicity of the point. And instead of having E square points, I have E square minus L1 minus L2 plus L2 plus LR, if I have R points. So this means that instead of having a map which is branched of degree E square, is branched of smaller degrees. Topologists hate this. Topologists want these numbers to be constant. I mean, the degree of a map is constant. Now this is an example of a simple algebraic map when the degree drops. And so, in principle, topologists go to sleep at this point of the lecture. They hate this. They hate this. But this is what's happening here. And so the thing is the following. If I take here a foliation here on this part over here, and I pull it back, then I only will have E squared minus L1 up to other copies of the thing. So the question is, where did the other copies go to? If I make a small perturbation of these maps, I can destroy this condition and I will get a map which is E squared to 1. And so the most critical situation of this, and that's actually where we began, is with what's called the Cremona map. The Cremona map is a very simple map which is written C0, C1, C0, C2, and C1, C2. And this goes from CP2 minus 3 points and it is 1 to 1. It has three points where it's not defined, and so these are the axis lines and the line at infinity, and so it's a biholomorphism of the complement of the three lines to the complement of the three lines, but it has degree 2. And so this means that if here I have a form of degree D, when I pull it back over here, it will have degree 2D minus 1. But then it's the same as this one because it's birational, it's bijective. And so for me it was a puzzle, and I said, how can this be that something which here has some degree, exactly the same picture appears here, but has bigger degree? It didn't make any sense because I said, it's supposedly that the higher the degree of the differential equation, the more complicated the differential equation is. And here we're seeing that this does not happen. So what we did is we put here plus tc2 squared plus 2c1 squared plus tc0 squared. And so we embedded this. So we have this one parameter. We have a copy of CP2. Here we have 0. Here we have a copy of CP2. And here we have a map F into same thing here over CP2. And so this is the nightmare of the topologist. Because see, this is a map which is 4 to 1, 4 to 1, 4 to 1. But when we arrive here, it's not defined at these 3 points, and it's 1 to 1. So, and then if we have an object here, so actually we first began with the Lefschetz vibration and pulled it back and said, let's see what happens with the Lefschetz vibration. And so we pulled back this situation over here, and then to make sense of this, we did the following thing. We are going to blow up these 3 points. See, this is a map, this F is a map which goes from T and then a point P, and then it says you keep the parameter T and then you put the Ft at the point P. And these are the equations. Now this is defined on C cross CP2 minus 0 times P0, P1, P2, minus 3 points, which are the base of the pencil, into C cross CP2. So, the topologist can relax because it's not a map defined on the 3 points. So what we did is we blew up the 3 points. So if we blow up the 3 points, what happens is that we're going to have a copy here is CP2 with the 3 points blown, and then here we have 3 copies of CP2, which are the planes. See, when you blow up a point in a 3-dimensional space, what you get is a CP2. But the CP2 is over 0. It doesn't spread over. It's not spread over. It's directly on top of 0. And so what happened is that if we took here the foliation omega, what happened is that here we did have 4 copies of f omega. One of them was the one we were seeing, and the other 3 copies, they were swallowed by the singular points. The singular points are swallowing a complete set of the foliation on CP2. And so, so here the picture comes out like this. The foliation over 0, if I look at the Lefschetz pencil, let me explain the Lefschetz pencil because it's simpler. So here I have these copies, 1, 2, and 3. So here I have my a fiber here, over here. And then here I have another fiber. And here I have another fiber. And here I have another fiber. So the pencil over the point 0 looks something like this. So here I have a Riemann surface of genus G. And here I have another copy of a Riemann surface of genus G, which is having these transverse intersections. Here I have another copy of this Riemann surface of genus G. And here I have another copy of this Riemann surface of genus G. This one has 3D points deleted. This one has D, this one has D, and this one has D. And if I look in the 3-dimensional space, here I have something that looks like this. So this is this, and this is this. And so when I perturb and put T different from 0, what happens is that this here I put a small neck, and so I'm making a vanishing cycle. So this means that we can understand the foliation, well, in this case, what's the left-shade pencil obtained by composing with the Cremona map is the union of 4 copies of the fibers of the original map, which have transverse intersections at these points. And then when we move the leaf a little bit, so it's a much more complicated fiber, because now it will have genus 4G plus the number so all these connections add also genus to the Riemann surface. And then in general, the picture will be exactly the same, in the sense that we will have a foliation in this leaf, in this CP2 blown up. We have this foliation, we will have a line, and then here we have another copy. And so instead of having these D points of intersection, we'll have an infinite number of points of intersection. And so we can understand the topology of the leaves formed by this general phi of f, and then phi of f prime and phi of f, where f has some fixed points. So these are base points. So this means that if we take the parameter t equal to 0, once we are for t different from 0, we can apply the previous theorem. And so to conclude here in this part, we have a theorem by the same authors that I mentioned that says that if one blows up conveniently, and we have a criterion of when it's convenient, then one can reconstruct the foliation phi star of ft of omega from phi f0 of omega blown up. So in the complement of 0, we have U equivalence, and in this more degenerate case, one has to blow up to bring up all the foliation. And I think we finish here. Thank you.
¿Hay preguntas?
Me los dejaron nadados.